The interrupted interstellar dream. In our modern world, we are surrounded by the hum of an invisible digital civilization. We have grown accustomed to the near-infinite computing power tucked away in our pockets, and we rarely look up to acknowledge the web of satellites that orchestrate our daily lives. But for this journey, I want you to strip away that noise. Let the frantic pulse of the 21st century fade into a low, steady thrum. We are recalibrating our internal clock. We are setting the coordinates of time back to December 14th, 1972. This was the final act of the Apollo 17 mission. Standing in the deep monochromatic shadows of the Taurus-Littrow Valley, Eugene Cernan became the last human being to ever walk the lunar surface. The moon, at that moment, was a world of absolute stillness. There is no wind to carry sound there. There is only the rhythmic, metallic thumping of one's own heart against the chest plate of a pressurized suit. Before he began the ascent, Cernan knelt in the fine, abrasive gray dust, a substance that feels like flour but cuts like glass. With a gloved finger, he traced 3 letters: TDC, the initials of his daughter, Tracy. He knew that in this airless vacuum, those letters might remain undisturbed for millions of years. A tiny, fragile monument to a father's love on a silent world. As the ascent engine ignited, casting a momentary majestic glow across the ancient craters, the moon shrank back into a lonely gray-white marble suspended in the infinite abyss. Cernan was carrying away more than just rock samples. He was carrying away 50 years of human interstellar ambition. For over 5 decades, the moon returned to its ancient, suffocating silence. Does it not strike you as a profound anomaly? In an age where we navigated by slide rules and hand-drawn charts, when a modern digital scale had more computing power than the entire NASA headquarters, we successfully crossed 380,000 kilometers of lethal vacuum. Today, our technology has advanced by a factor of millions, yet no new human footprint has been added to that dust. This isn't just a pause. It is a fracture in the timeline of human progress. Usually, in our history, once a trade route is opened, it stays open. Once the Industrial Revolution began, the gears never stopped turning, except for space. After taking our first tentative steps out of the planetary cradle, we suddenly sat back down. The silence that followed was not empty. It was a period of reflection. We realized that the Apollo missions were a feverish, beautiful, and terrifyingly expensive sprint, fueled by the existential shadows of a divided world. It was a glorious beginning, but it lacked the infrastructure to stay. This 50-year silence was a necessary gestation period. We have spent this time in the shallows of low Earth orbit, aboard the International Space Station, learning the biological price of the void. We have been waiting for the moment when returning to the moon isn't just a display of power, but a sustainable expansion of our species. To appreciate the brilliance of the moon, we must first look at the profound lessons learned at the very beginning of the journey. Every great endeavor in human history has its crucible, a moment where the cost of ambition is measured against the fragility of life. For the Apollo program, that moment came on January 27, 1967, at Launch Complex 34 in Cape Canaveral. The mission for Apollo 1 was undergoing a routine ground test. The 3 pioneers inside, Virgil Gus Grissom, Edward White, and Roger Chaffee, were the embodiment of the explorer's spirit. At that stage of engineering, the design choices were bold but carried inherent risks. One such choice was the use of a pressurized, pure oxygen environment within the cabin. In the context of the 1960s, this was seen as an elegant engineering solution to reduce the ship's weight. However, the laws of chemistry are unforgiving in the void. During the test, a technical failure led to a sudden and uncontrollable fire that swept through the cabin. Because of the engineering standards of the time, the hatch was designed to open inward, which made emergency exit impossible under the intense internal pressure of the event. In a matter of moments, the mission ended in a heavy, heart-wrenching silence. This event did not just spark a national mourning. It ignited a total revolution in aerospace safety. The public and the scientific community paused to ask, how do we reach for the stars without losing our humanity? NASA's response was a testament to the resilience of the human intellect. Over the next 20 months, they tore apart every single design blueprint. They developed entirely new, fire-resistant materials and re-engineered the hatch to blast open outward in less than 5 seconds. They realized that in the vacuum of space, optimal engineering must always be synonymous with redundant safety. This crucible transformed Apollo from a daring experiment into a robust, world-changing system. Every success that followed, every footprint on the lunar dust, and every safe return to Earth was built upon the hard-won wisdom of those who had paved the way. We learned that the path to the moon is not just paved with fuel and fire, but with an unwavering commitment to protect the lives of those who dare to leave the cradle. To appreciate the brilliance of the moon, we must first look at the profound lessons learned at the very beginning of the journey. Every great endeavor in human history has its crucible, a moment where the cost of ambition is measured against the fragility of life. For the Apollo program, that moment came on January 27, 1967, at Launch Complex 34 in Cape Canaveral. The mission for Apollo 1 was undergoing a routine ground test. The 3 pioneers inside, Virgil Gus Grissom, Edward White, and Roger Chaffee, were the embodiment of the explorer's spirit. At that stage of engineering, the design choices were bold but carried inherent risks. One such choice was the use of a pressurized, pure oxygen environment within the cabin. In the context of the 1960s, this was seen as an elegant engineering solution to reduce the ship's weight. However, the laws of chemistry are unforgiving in the void. During the test, a technical failure led to a sudden and uncontrollable fire that swept through the cabin. Because of the engineering standards of the time, the hatch was designed to open inward, which made emergency exit impossible under the intense internal pressure of the event. In a matter of moments, the mission ended in a heavy, heart-wrenching silence. This event did not just spark a national mourning. It ignited a total revolution in aerospace safety. The public and the scientific community paused to ask, how do we reach for the stars without losing our humanity? NASA's response was a testament to the resilience of the human intellect. Over the next 20 months, they tore apart every single design blueprint. They developed entirely new, fire-resistant materials and re-engineered the hatch to blast open outward in less than 5 seconds. They realized that in the vacuum of space, optimal engineering must always be synonymous with redundant safety. This crucible transformed Apollo from a daring experiment into a robust, world-changing system. Every success that followed, every footprint on the lunar dust, and every safe return to Earth was built upon the hard-won wisdom of those who had paved the way. We learned that the path to the moon is not just paved with fuel and fire, but with an unwavering commitment to protect the lives of those who dare to leave the cradle. In the quiet aftermath of reconstruction, humanity turned its gaze back to the launch pad, where a giant was being awakened. To understand the sheer scale of the return to flight, one must understand the man who held the keys to the heavy gates of gravity. Wernher von Braun. A man of deep historical complexity, he was possessed by a singular, unyielding obsession, the transcendence of the human spirit through the conquest of space. He viewed the heavens not as a distant mystery, but as a destination that required a massive, physical sacrifice of energy. His crowning achievement, the Saturn V rocket, was more than a machine. It was an iron cathedral, built to challenge the heavens. If you were to stand at its base, you would feel a crushing sense of insignificance. Rising 36 stories into the Florida sky, It stood taller than the Statue of Liberty. It was a monolith of white-painted aluminum, containing over 3 million individual parts, all harmonized to perform a single, violent symphony of propulsion. When those 5 F1 engines ignited, the world beneath them ceased to exist. They unleashed a staggering 3,400 tons of thrust, a force so immense that it translated into the power of 85 Hoover dams. To fuel this ascent, the rocket incinerated 13 tons of kerosene and liquid oxygen every single second. The sound was not merely heard. It was felt in the very marrow of one's bones. It was a physical wall of acoustic energy that vibrated the earth itself, shaking buildings miles away. This was the moment humanity used the raw, primal power of controlled explosions to punch a jagged hole through the Earth's heavy atmospheric veil. Von Braun had successfully turned the engines of destruction into a ladder to the stars. But the true revelation of the Apollo program did not come from the moon's gray surface. It came from looking back. On December 24, 1968, the crew of Apollo 8 became the first humans to leave the gravitational embrace of Earth and orbit another celestial body. As they emerged from the dark, silent shadows of the lunar far side, they witnessed a sight that would forever alter the collective consciousness of our species. Earthrise. Floating above the jagged, desolate, and lifeless lunar horizon, a vibrant, sapphire blue marble emerged from the eternal blackness. It was our home, fragile, lonely, and breathtakingly beautiful. In that singular moment, captured in a photograph that would define a century, humanity realized a profound truth. We saw that our world was not an infinite expanse of borders and battlefields, but a tiny, solitary ark sailing through a vast, unforgiving cosmic ocean. This perspective, the overview effect, triggered a global awakening. We realized that if we could not yet survive on the barren lunar plains, we had to protect the only oasis we had ever known. The mission to the moon had unexpectedly taught us the value of the Earth. It was a moment of profound humility, a realization that in the grand tapestry of the cosmos, we are all travelers on the same fragile vessel, bound together by the thin, shimmering ribbon of our atmosphere. July 20th, 1969. The lunar module, a fragile-looking craft aptly named the Eagle, had separated from the command module and was drifting toward the lunar dust. But the universe is a jealous guardian of its secrets, and it does not yield to intruders without a fight. As the Eagle descended to an altitude of 10,000 meters, the silence inside the cabin was broken by the sharp, persistent chirping of an alarm. On the primitive instrument panel, a yellow light flickered. 12:02. Then, 12:01. These were executive overflows. The onboard guidance computer, a machine with less processing power than a modern-day thermostat, was being choked by data. It was struggling to decide which tasks were critical for survival and which could be discarded. In Houston, the mission controllers held their collective breath. A 24-year-old technician made the split-second call. "We're go" on that alarm. It was a decision that rested on the thin line between immortality and catastrophe. But the real trial was yet to come. As Neil Armstrong looked through the small, triangular window at an altitude of only 150 meters, his heart rate spiked. The automated guidance system, confused by the lunar terrain, was steering them directly into a boulder field, a chaotic graveyard of rocks the size of cars. Landing there would mean a shattered landing leg, a tipped-over ship, and a slow, agonizing death on a world with no air. With the coolness of a man who had stared death in the face many times as a test pilot, Armstrong flipped the switch to manual. He tilted the Eagle forward, using the last of his momentum to surf over the treacherous terrain. He was searching for a patch of gray that was smooth enough to cradle the ship. In Houston, the voice of the capsule communicator crackled with a terrifying, rhythmic intensity. 60 seconds of fuel remaining. The Eagle was now hovering, its single descent engine kicking up a ghostly, blinding storm of lunar dust. In the vacuum, this dust does not billow like smoke. It sprays out in straight, jagged lines, obscuring the horizon and stealing the pilot's sense of motion. 30 seconds. The fuel gauges were dipping into the dead zone. If the engine cut out now, they would drop like a stone. Armstrong felt for the ground through the soles of his boots. Suddenly, a faint blue light flickered on the dashboard. Contact. Houston. Tranquility Base here. The Eagle has landed. That night, the world watched in a hypnotic trance. It wasn't just a triumph of silicon and steel. It was a victory of human intuition over the limits of the machine. Yet, as quickly as the fire of the Apollo era had ignited, it began to flicker. By 1972, the political fervor that had fueled the moon race began to cool under the shadow of economic recession and shifting global priorities. The moon, once the ultimate prize, was suddenly viewed as a magnificent desolation that was too expensive to maintain. We retreated to the familiar embrace of Earth, and for 5 decades, the lunar dust remained undisturbed by human feet. But we must not mistake this absence for stagnation. While the moon slept, humanity was building a bridge in the shallows of space. We spent those 50 years constructing and living aboard the International Space Station. Many critics dismissed the ISS as a white elephant in orbit, a floating laboratory with no clear destination. But they were wrong. The space station was the crucible where we learned the fundamental laws of extraterrestrial survival. Inside that pressurized tin can, orbiting 400 kilometers above our heads, we spent over 20 years perfecting the closed-loop systems. We learned how to recycle 98% of all water, including the sweat and urine of the crew, and turn it back into pure, life-sustaining hydration. We studied the way cosmic radiation attacks human DNA and developed the shielding necessary to survive the journey to deep space. We watched as astronauts' bones grew brittle and their muscles withered in zero gravity. And we engineered the grueling exercise regimes required to keep the human frame intact. We weren't just circling the Earth. We were sharpening our blades. We were turning the art of space travel into a sustainable science. The International Space Station was the rehearsal for the main event. Now, as the station nears the end of its operational life, we are no longer the frightened children who took a frantic leap to the moon in 1969. We are a species that has learned to live, work, and thrive in the void. And so, we turn our gaze back to the moon, not as a place to visit for a few hours of glory, but as a place to stay. The long night is over. The dawn of the Artemis era is here. As we move past the era of mere footprints, we enter the era of the Great Lunar Scramble. To understand this, we must look at the geography of the lunar South Pole, a place as valuable and contested as any oil field or mountain of gold ever found on Earth. This is the new Malacca Strait of the solar system. In the deep, eternal shadows of craters like Shackleton and Amundsen, where the sun hasn't shone for 2 billion years, lies the liquid gold of the cosmos. Water, ice. To a lunar explorer, water is not just for drinking. Through the process of electrolysis, it is the source of oxygen for breathing and liquid hydrogen for rocket fuel. Imagine the strategic tension. Just a few kilometers away from these frozen abysses are the peaks of eternal light, high ridges that are bathed in near-constant sunlight. These ridges are the only places in the solar system where a solar panel can provide power almost 24/7. This proximity, infinite energy right next to infinite fuel, creates a geopolitical flashpoint. Even though the Outer Space Treaty of 1967 forbids nations from claiming the moon, a new de facto rule is emerging: the logic of presence. Whoever builds the first solar array on those ridges and the first mining drone in those craters effectively controls the pulse of the lunar economy. It is a silent, high-stakes game of chess played over a distance of 380,000 kilometers. For 50 years, the moon was locked behind a door of prohibitive costs. We must talk about the gravity tax. To launch a single kilogram of cargo from Earth to the moon using traditional rockets cost roughly $1 million. At those prices, the moon was a playground for governments, not a site for industry. Enter the SpaceX Starship. To understand its impact, you must visualize a stainless steel monster standing 120 meters tall. Unlike the Saturn V, which was a magnificent single-use machine, the Starship is designed for total reusability. Imagine if every time you flew from London to New York, the airline scrapped the Boeing 747 upon arrival. That was the old way of spaceflight. Starship changes the fundamental math of the universe. By landing both the booster and the ship back on the launch pad, the cost of space travel drops from billions of dollars to the price of the propellant alone. This is the logistics revolution that turns the moon into a reachable suburb. With a payload capacity of 100 tons, we are no longer sending tiny probes. We are sending entire cities, oxygen factories, and shielding modules in a single flight. Starship is the interstellar bus service that finally breaks the shackles of the gravity well. But why are we staying? Our home planet is shielded by a thick atmosphere and a powerful magnetic field, which protects us from the solar wind, but also prevents helium-3 from reaching our soil. The moon, however, has no such shield. For 4 billion years, it has been acting as a giant cosmic sponge, soaking up this rare isotope from the sun. Helium-3 is the holy grail of clean energy. It is the perfect fuel for nuclear fusion. Unlike the fusion reactions we attempt on Earth today, a helium-3 reaction produces virtually no radioactive waste. It is pure, limitless energy. A single Starship cargo bay filled with 100 tons of helium-3 could theoretically provide enough energy to power the entire United States for a full year. The moon is not just a barren rock. It is the power plant of the 22nd century. The nations and corporations that secure the primary mining rights to the lunar regolith will hold the keys to the future of the global energy market. We are witnessing a transition from the era of fossil fuels to the era of lunar energy, where the dust of another world will light the cities of our own. Finally, we must consider the human cost of this expansion, as the first permanent bases are established deep within the lunar lava tubes. Natural volcanic tunnels that protect inhabitants from deadly cosmic radiation. A new class of human will be born. The selenite. A child born on the moon will grow up in 1/6 of Earth's gravity. Their heart will not have to pump as hard. Their bones will not feel the same crushing weight. Over generations, their physiology will change. They will grow taller and more slender. Their perception of space and movement will be fundamentally different from ours. To a selenite, the Earth will not be home. It will be that heavy, bright, and suffocatingly dense marble hanging in the black sky. A place where they can never easily visit because their hearts and bones would collapse under the standard gravity. This is the first true speciation of humanity. We are dividing into two classes. The terrestrials, bound by the heavy chains of Earth, and the selenites, the light, agile scouts of the solar system. As you listen to the low hum of this narrative, imagine the first lunar city. It is a world of recycled air, of hydroponic gardens glowing under purple LEDs, and of a silence so deep it feels physical. The moon is no longer a destination. It is the beginning of our life as a multiplanetary species. Before we dive into the cold equations of mass and velocity, let us contemplate the moon as a singular presence. For as long as our ancestors have looked upward, the moon has been the silent sentinel of our nights, a pale, cratered ghost that orchestrates the tides of our oceans and the biological rhythms of our lives. But what is this object? It is not merely a rock in the sky. It is a planetary mass body, a world that exists in a state of magnificent desolation. The moon is the fifth largest natural satellite in our solar system. Yet its relationship with its parent planet, our Earth, is unique. Nowhere else in the inner solar system do we find a satellite so large in proportion to its planet. This realization forces us to ask, is the moon a captured wanderer from the deep dark? Or is it a piece of our own flesh and bone, torn away in a moment of primordial violence? As we begin this journey, let your mind drift across the 380,000 kilometers of vacuum that separate us, and prepare to deconstruct the very foundation of this silver sphere. The question of how the moon began is the greatest detective story in the history of science. For decades, researchers proposed the capture theory, suggesting the moon was a wandering rogue planet snared by Earth's gravity. Others championed the fission theory, imagining a young, rapidly spinning Earth, flinging a piece of itself into orbit. But the evidence from the lunar dust tells a different, more violent story. Today, the prevailing consensus is the giant impact hypothesis, also known as the Theia event. Imagine the solar system 4.5 billion years ago, a chaotic shooting gallery of protoplanets. A world the size of Mars, named Theia, was on a collision course with the infant Earth. The impact was not a glancing blow, but a cataclysmic merger. The energy released was enough to liquefy both worlds, sending a colossal ring of incandescent debris into orbit. Over a period of mere months or years, this ring of molten rock and metal coalesced, cooled, and hardened into the sphere we now call the moon. We are, in a very literal sense, children of the same fire. The turning point in our understanding came when we finally touched the lunar surface. The 382 kilograms of lunar rock and soil, the regolith brought back by the Apollo missions, provided the DNA of the moon. When scientists analyzed these samples in the lab, they discovered something staggering. The isotopic signatures of oxygen in lunar rocks are virtually identical to those on Earth. This was the smoking gun for the giant impact. If the moon had been captured from another part of the solar system, it would have a different chemical fingerprint. Instead, we found that the moon is made of the same fundamental materials as the Earth's mantle. However, there was one glaring difference. The moon is incredibly dry. It lacks volatiles, elements like water and nitrogen that evaporate easily. This suggests that the moon was born in a high-temperature inferno so intense that it baked the water right out of the rocks. When you look at the moon, you are looking at an Earth that was once purged by fire. To comprehend the moon, we must speak of its physical presence. The moon's mass is approximately 7.3, 4 times 10, to the 22nd power kilograms. While that sounds immense, it is only about 1.2% of the Earth's mass. It is a lightweight world, a sphere with a diameter of 3,474 kilometers, roughly the width of the Australian continent. Because of this lower mass, the moon's gravity is only 1/6 of what we feel on Earth. On the moon, the escape velocity is significantly lower, which is why it is the perfect staging ground for deep space missions. But this low mass also means the moon could never hold onto an atmosphere. Any gas that might have escaped from its interior billions of years ago simply drifted away into the void. The moon is a world without a blanket, exposed forever to the harsh radiation of the sun and the freezing vacuum of the cosmos. For a long time, we viewed the moon as a solid, uniform ball of rock. But seismic data from the Apollo-era moonquake sensors revealed a complex, layered anatomy. Like the Earth, the moon has a crust, a mantle, and a core, but the proportions are vastly different. The lunar crust is a layer of anorthosite rock, ranging from 60 to 100 kilometers thick. Beneath this lies the massive mantle, composed of minerals like olivine and pyroxene. But as we go deeper, the mystery intensifies. The moon's overall density is much lower than Earth's, which led scientists to a startling conclusion. The moon's iron core is remarkably small, while the Earth's core makes up about 30% of its mass. The moon's core is estimated to be less than 1 or 2%. This is the final piece of the giant impact puzzle. The heavy iron from the impactor stayed with the Earth, while only the lighter, rocky debris escaped to form the moon. Is the moon truly a dead world? For decades, the answer was a definitive yes. We believed the moon had cooled completely, its internal fires extinguished billions of years ago. But modern reanalysis of seismic data suggests a more nuanced reality. The moon does have a core, approximately 500 kilometers in diameter, and it is not a solid block of ice-cold iron. Evidence suggests the moon has a solid inner core surrounded by a fluid outer core layer. While it lacks the vigorous convection currents that generate Earth's powerful magnetic field, there is still heat trapped down there, a lingering, primordial warmth. The moon is not dead in the sense of being an inert rock. It is in a state of terminal cooling. There are still moonquakes triggered by the Earth's tidal pull, stretching and squeezing the lunar interior like a piece of clay. The moon is a ghost world, yes, but it is a ghost with a faint, lingering heartbeat. A reminder of the violent, molten era when it was a sea of magma orbiting a glowing infant Earth. When we weigh the moon against the other terrestrial bodies in our solar system, we encounter a profound scientific puzzle known as the density paradox. Earth has an average density of 5.5 grams per cubic centimeter, largely due to its massive, churning iron core. The moon, by contrast, has a density of only 3.3 grams per cubic centimeter. This discrepancy tells us that the moon is missing something vital. While the Earth is a heavy, metal-rich planet, the moon is primarily composed of silicate rock, the same material found in the Earth's outer mantle and crust. Geologists have calculated that the lunar iron core is likely no more than 300 to 400 kilometers in radius. This represents only about 1 to 2% of the moon's total mass. In contrast, the Earth's core accounts for nearly 32% of its mass. This iron deficiency is one of the strongest pieces of evidence for the giant impact theory. It suggests that when the protoplanet Theia struck the Earth, the iron cores of both worlds merged and sank into the center of the Earth, while only the lighter, rocky outer layers were splashed into orbit to form the moon. The moon, in essence, is a planet born without its heart. Shortly after the moon coalesced from the debris of the impact, it was not the cold, gray world we see today. It was a glowing, incandescent sphere, covered by a global magma ocean, thousands of kilometers deep. This sea of molten rock existed for millions of years. In the low gravity of the young moon, a unique geological sorting occurred. As the magma ocean began to cool, heavier minerals like olivine and pyroxene sank toward the interior to form the mantle. Meanwhile, lighter minerals, specifically a white rock called anorthosite, floated to the surface like icebergs in a dark sea. These floating rocks eventually merged to form the primary lunar crust, the bright white areas we see from Earth today, known as the lunar highlands. This crystalline crust is over 4 billion years old, making it some of the oldest preserved planetary surface in the entire solar system. When you look at the bright parts of the moon, you are looking at the frozen remnants of a primordial fire. The moon's face is a map of its traumatic childhood. Approximately 4 billion years ago, a period known as the Late Heavy Bombardment reshaped the lunar surface. Giant asteroids, some the size of small cities, rained down upon the moon with unimaginable force. These impacts were so violent they cracked the lunar crust, reaching deep into the still warm mantle. Millions of years later, as radioactive decay heated the interior, Vast quantities of basaltic lava erupted through these cracks, flooding the deepest impact basins. When this lava cooled and solidified, it created the dark, smooth plains we call Maria, the Latin word for seas. These are the man in the moon features. Unlike the ancient highlands, the Maria are younger, smoother, and rich in iron. They represent a secondary era of lunar evolution, a time when the moon was still geologically active enough to bleed lava into its own wounds. One of the most profound characteristics of the moon is what it lacks: an atmosphere. Without enough mass to generate sufficient gravity, the moon cannot hold onto a blanket of air. This creates an environment of absolute vacuum. However, the moon is not entirely airless. It possesses what scientists call an exosphere, a layer of gases so thin that the atoms rarely even collide with one another. This exosphere is composed of trace amounts of helium, neon, and even sodium and potassium kicked up by the solar wind. Because there is no atmosphere to scatter light, the lunar sky is always a deep, terrifying black. Even when the sun is shining directly overhead, there is no weather on the moon, no wind to whisper through the craters, no rain to wash the dust. This lack of atmosphere means that temperature swings are extreme, leaping from 127 degrees Celsius in the sun to minus 173 degrees in the shade. It is a world of thermal violence, where every shadow is a wall of ice, and every sunlit patch is a furnace. Today, the moon has no global magnetic field. It cannot protect itself from the solar wind, nor can it provide a compass for travelers. But the rocks brought back by Apollo tell a different story. Analysis of these samples shows that they were once magnetized, suggesting that billions of years ago, the moon had a lunar dynamo, a churning, molten core that generated a magnetic field, perhaps even stronger than the Earth's current field. How could such a small world generate such a powerful shield? This is a subject of intense debate. Some scientists believe the moon's core was stirred by the Earth's gravity during a time when the moon was much closer to us. As the moon drifted away over eons, this gravitational stirring weakened, and the lunar dynamo died. The moon's magnetic field did not just vanish. It froze into the rocks of the crust, leaving behind magnetic anomalies, ghostly remnants of a shield that once guarded a much younger, more active world. Due to a phenomenon called tidal locking, the moon always shows the same face to the Earth. For almost all of human history, the far side was a realm of pure mystery. It wasn't until 1959, when the Soviet Luna 3 probe circled the moon, that we saw it for the first time. To our surprise, the far side looks nothing like the side we see. It almost entirely lacks the dark, smooth Maria. Instead, it is a rugged, mountainous, and heavily cratered landscape with some of the thickest crust on the moon. This asymmetry remains one of the moon's great unsolved mysteries. Some believe that the Earth's heat, radiating toward the near side when the moon was still molten, prevented the crust from thickening there, while the far side cooled and hardened much faster. The far side is a wild, untamed wilderness, a silent record of the solar system's violent history, shielded forever from the radio noise and gaze of Earth.
For 50 years, the scientific community lived under a rigid, unbreakable dogma. The moon is a total desert. This was not a guess. It was based on the ironclad evidence of the Apollo era. When scientists analyzed the rocks brought back in the 1970s, they found them to be bone dry. There were no hydrous minerals, no clays, and no evidence that water had ever played a role in lunar geology. This made sense within the giant impact theory. If the moon was born from a titanic collision that liquefied rock, any water should have been boiled away into the vacuum. For decades, the moon was taught in textbooks as a world of magnificent desolation, a place where a single drop of water was as impossible as a breath of air. This belief dictated our entire strategy. We thought we had to bring every gram of life support from Earth, but the moon was hiding a secret in its longest shadows. waiting for us to stop looking at the rocks and start looking at the darkness. To find water, we had to understand the unique geometry of the lunar poles. Because the moon's axis is almost perfectly upright, tilted at only 1.5 degrees, the sun always hangs near the horizon at the poles. In deep impact craters like Cabeus or Shackleton, the crater floors never see a single photon of sunlight. These are the permanently shadowed regions. In these cold traps, temperatures haven't changed for 2 billion years, hovering around -230 degrees Celsius colder than the surface of Pluto. The physics here is profound. If a stray water molecule, perhaps delivered by a comet, or created by the solar wind, happens to bounce into one of these craters, it instantly freezes and becomes thermally trapped. Without sunlight to energize it, that molecule can never leave. Over eons, these craters became the solar system's most patient collectors, slowly accumulating a frozen treasure, molecule by molecule, hidden in a darkness so thick that even the Earth's best telescopes could not see it. The first crack in the dry moon dogma came in 1994, not with a landing, but with a radar beam. A small, joint NASA military probe named Clementine sent radio waves into the shadowed craters of the South Pole. When the waves bounced back, the bistatic radar experiment showed a signature that looked suspiciously like ice. It was a faint whisper, a statistical anomaly that divided the scientific world. Critics argued it was just the rough texture of crater walls. The debate raged for years. The moon remained an enigma. Was it a desert, or was there an icy oasis at its heart? We needed a more violent proof. We needed to physically strike the moon to see what it was hiding. On October 9th, 2009, humanity decided to stop guessing. NASA launched the LCROSS mission, Lunar Crater Observation and Sensing Satellite. The plan was brutal and brilliant. They would crash a 2,000-kilogram spent rocket stage directly into the Cabeus crater at over 9,000 kilometers per hour. A second spacecraft followed closely behind, flying through the resulting debris plume with its spectrometers ready. As the plume of dust rose 10 kilometers above the crater floor, the instruments detected the unmistakable signature of water vapor and ice crystals. The impact revealed that some crater floors are composed of up to 5% water ice. It wasn't just a few molecules, it was a reservoir. This was the moment the second space race truly began. We realized that the moon was not a dead end, but a gas station in the sky. The presence of water changed the moon from a place we visit to a place we can inhabit. Where did this water come from? The prehistory of lunar water is a story of cosmic delivery. Some of it arrived via carbonaceous chondrites, primitive asteroids, and comets that struck the moon during its violent infancy. But there is another, more subtle source: solar alchemy. The sun constantly blasts the moon with protons, hydrogen nuclei. When these protons strike the oxygen-rich lunar soil, a chemical reaction occurs, creating hydroxyl and water. This means the moon is breathing a tiny amount of water into existence every single day. The moon is not just a passive rock. It is an active chemical laboratory. This water migrates across the surface, hopping like invisible ghosts until it finds the safety of the cold traps. Understanding this cycle is the key to our future. It means the moon is a renewable resource, a world that is constantly being refueled by the stars themselves. To close the loop on the lunar water narrative, we must understand why this discovery dictates the next 100 years of human history. On Earth, water is life. In space, water is power. Transporting 1 liter of water from Earth to the moon costs tens of thousands of dollars. But if we can live off the land, the economics of space travel are revolutionized. By splitting water into hydrogen and oxygen, we create the most powerful chemical rocket propellant known to science. The moon's south pole is now the most strategic territory in the solar system. It is the oil field of the future. The nation that masters the extraction of lunar ice will control the high ground of space. They will possess the fuel to reach Mars, the oxygen to sustain cities, and the water to grow forests inside lunar domes. The discovery of water didn't just change our science. It gave humanity a permanent home in the void. To understand the moon, we must travel back 4.5 billion years, to a time when the solar system was not a stable clockwork, but a chaotic shooting gallery of protoplanets. This is the story of the giant impact hypothesis, the most widely accepted explanation for our moon's existence. But it is a story that begins with a tragedy of cosmic proportions. Imagine a young Earth, still molten and glowing, and a rogue world named Theia, roughly the size of Mars, on a collision course. This was not a glancing blow. It was a cataclysmic merger. The impact was so violent that it pulverized Theia and stripped away a massive portion of the Earth's outer mantle. For a brief period, the Earth was surrounded by a glowing, incandescent ring of debris, a disk of vaporized rock and metal. Over a few short centuries, gravity acted as a silent architect, pulling this debris together, cooling it, and molding it into the sphere we now call the moon. We are, in a very literal sense, children of the same fire. The moon is not a stranger caught in our gravity. It is a piece of our own world, cast out into the dark. The legacy of that violent birth is written in the moon's internal structure. If the moon were a typical planet, it would have a massive, iron-rich heart like the Earth. But the moon is different. It is a world characterized by the density paradox. While the Earth is heavy and metallic, the moon is primarily composed of silicate rock, the lighter material found in the Earth's outer layers. As we peel back the layers of the moon, we find a crust of anorthosite, a white, crystalline rock that floated to the surface of a lunar magma ocean billions of years ago. Beneath the crust lies a thick, rigid mantle of olivine. But as we reach the center, we find a startling truth. The moon's iron core is remarkably small, representing less than 2% of its mass. This is the smoking gun of the giant impact. During the collision, the heavy iron cores of both worlds merged and sank into the Earth, leaving only the lighter, rocky crumbs to form the moon. The moon is a planet that was born without a heart, a silent record of a primordial theft. Today, the moon is a defenseless world, constantly battered by the solar wind. It lacks a global magnetic field to shield its surface. But it wasn't always this way. When the Apollo astronauts brought back lunar rocks, scientists discovered something that challenged our understanding of planetary life. These rocks were magnetized. This implies that billions of years ago, the moon possessed a lunar dynamo, a churning, molten core that generated a powerful magnetic shield. The life of the moon's core was short but intense. Some theorists suggest that because the moon was much closer to the Earth in its infancy, our planet's gravity stirred the lunar interior like a spoon in a cup of coffee, keeping the core molten and active. But as the moon slowly drifted away, at a rate of about 4 centimeters per year, that stirring force weakened. The internal fires began to cool, the dynamo slowed, and eventually, the magnetic shield vanished. The moon didn't just lose its air, it lost its protection, becoming a ghost world where the only remaining magnetism is frozen into the rocks, a haunting memory of a time when the moon was as alive as the Earth. Now, we turn from the moon's past to its role as the savior of our future. Because the moon lost its magnetic shield billions of years ago, its surface has been relentlessly bombarded by the solar wind. For 4 billion years, the sun has been painting the lunar regolith with a rare and precious isotope, helium-3. On Earth, helium-3 is almost impossible to find, shielded from us by our atmosphere. But on the moon, it is abundant, trapped within the top layers of the lunar dust. This is the ultimate cosmic alchemy. Helium-3 is the holy grail of clean energy, the perfect fuel for nuclear fusion. Unlike the fusion we attempt on Earth today, which creates radioactive waste, a helium-3 reaction is clean, safe, and nearly limitless. Imagine a future where massive automated harvesters roam the lunar plains, sifting through the dust to extract this solar treasure. A single Starship cargo bay filled with 100 tons of helium-3 could power the entire United States for a full year. The moon, once a silent witness to our history, is destined to become the power plant of the 22nd century. The very dust that was born from an ancient collision will one day light the cities of the world that gave it birth. As we conclude this exploration of the moon's life cycle, we must look at its final role, the digital arc of humanity. In a world increasingly dependent on fragile digital networks, the moon offers something the Earth cannot perfect: frozen stability. Deep within the lunar lava tubes, where the temperature never changes and the radiation cannot reach, we are planning to build the ultimate backup for human civilization. These massive basaltic cathedrals will house the lunar supercomputing centers. Because the moon is geologically quiet and thermally stable, it is the perfect place to store every piece of art, every genetic sequence, and every scientific discovery humanity has ever made. This is the full circle of our relationship with the moon. It was born from our flesh, it witnessed our evolution, and now it will become the guardian of our legacy. If a catastrophe were to strike the Earth, the second server on the moon would remain a silent, silver library, orbiting in the dark, waiting to teach a future generation who we were and how we reached for the stars. To understand the profound isolation of the moon, we must look through the eyes of the command module. Pilots, the men like Michael Collins and Al Worden, who stayed behind in orbit while their companions walked the surface. Each time their spacecraft drifted behind the lunar far side, they entered a realm known as the dark side of the moon, not because it lacked sunlight, but because it was totally severed from the human race. For approximately 48 minutes of every 2-hour orbit, the bulk of the moon acted as a massive solid barrier, blocking all radio waves from Earth. In these minutes, the silence was absolute. There was no crackle of static from Houston, no voices of friends, only the steady, mechanical hum of the life support system and the rhythmic breathing of a solitary human being. It was during these moments of total severance that astronauts witnessed a sight that no telescope on Earth could ever capture. As they transitioned from the deep, velvet blackness of the lunar night, they would see the sun's rays striking a jagged, high-altitude peak on the far side, a tiny, brilliant sliver of light, illuminating a wilderness of craters that had remained hidden from human eyes for millions of years. This visual confirmation of the moon's other face raised a haunting scientific question. Why is it that this entire hemisphere, comprising half of an entire world, is perpetually turned away from the cradle of humanity? The reason we never see the far side of the moon is not a coincidence of nature. It is the result of a multi-billion-year cosmic struggle known as tidal locking. To understand this, we must go back to the moon's infancy, when it was much closer to the Earth. In those early eons, the moon spun much faster on its axis, but the Earth is a heavy, dominant neighbor. Its gravity created tidal bulges in the moon, not just in its water, but in its very rock. Earth's gravity literally stretched the moon into a slight lemon shape. As the moon rotated, these bulges were constantly being pulled back by Earth's gravity, creating a form of gravitational friction. This friction acted like a set of cosmic brakes, slowing the moon's rotation century after century. Eventually, the moon's rotation slowed until it perfectly matched the time it took to orbit the Earth. This state of equilibrium is what we call synchronous rotation. Today, the moon takes exactly 27.3 days to spin once on its axis, and exactly 27.3 days to complete one orbit around us. The moon has been locked in a permanent, face-to-face embrace with its mother planet, forced to keep one side forever in our gaze, and the other forever in the dark. This tidal locking created the greatest logistical nightmare of the Apollo era, the communication blackout. In the 1960s, if a crisis occurred while the astronauts were behind the moon, Houston would be powerless to help. This forced the development of a unique form of autonomous engineering. The astronauts had to be trained to manage the most critical moments of the mission, such as the lunar orbit insertion burn, in total silence. They had to trust their onboard computers, and their own intuition, knowing that if the engine failed to fire or if it fired for too long, they would either crash into the lunar surface or be flung out into the infinite void of deep space, with no one on Earth even knowing they were in trouble until the silence was supposed to end. How did we overcome this? In the short term, it was through the sheer courage and meticulous training of the crews. But for the future, for our permanent return, we are building a new infrastructure. We are launching relay satellites like the Chinese Queqiao, which sit in a special gravitational balance point called the Lagrange point L2, hovering far behind the moon. These satellites act as a digital bridge, catching signals from the far side and bouncing them back to Earth. We are finally unlocking the far side. What was once a realm of terrifying silence is becoming the most sought-after territory for the next generation of deep space telescopes, because the same tidal locking that hides the far side from our eyes also shields it from all the radio noise and electronic interference of Earth. The zone of silence is becoming our clearest window into the birth of the universe. As the Apollo astronauts emerged from the radio silence of the far side, they didn't just notice the darkness, they noticed a profound geological shock. The moon we see from Earth, the near side, is defined by its vast, dark, and smooth plains. These are the Maria, ancient basins filled with frozen basaltic lava. But as they looked down at the far side, they saw a world that was almost unrecognizable. It was a chaotic, rugged wilderness of high-altitude craters and jagged mountains, almost entirely devoid of the smooth, dark seas that define our night sky. This is known as the lunar crustal asymmetry. For decades, this discrepancy remained one of the most baffling mysteries in planetary science. Why did one side experience massive volcanic eruptions and heal its wounds, while the other remained a scarred and frozen fortress of ancient, thickened rock? This duality is not an accident. It is the result of a delicate gravitational and thermal dance between the Earth and the Moon during their shared infancy. The answer to this mystery lies in the deep relationship between the two worlds shortly after the giant impact. At that moment, the Moon was much closer to the Earth than it is today, perhaps only 20,000 kilometers away. The Earth was still a glowing incandescent ball of magma, radiating immense heat toward the side of the Moon that was permanently turned toward it. Because the Moon was already tidally locked, its near side was constantly baked by the Earth's hellish glow, preventing the lunar crust from thickening. Meanwhile, the far side, facing the freezing void of deep space, was able to cool and solidify much faster. As a result, the far side developed a much thicker, reinforced crust. Millions of years later, when massive asteroids struck the Moon during the late heavy bombardment, they were able to puncture the thin crust of the near side, allowing the molten mantle to bleed out and fill the basins with lava. On the far side, however, the crust was so thick that even the most violent impacts could not draw lava from the interior. The man in the Moon we see tonight is a direct result of the Earth's ancient warmth, a permanent shadow of our planet's fiery beginnings. The unique nature of the lunar far side has created the most precious scientific sanctuary in the solar system, the zone of radio silence. Because the bulk of the Moon acts as a massive shield, blocking all the electronic noise, television signals, and radio interference generated by human civilization on Earth, the far side is the quietest place in the known universe. For radio astronomy, in the coming decades, the far side will host the Lunar Far Side Radio Array, unhindered by Earth's atmosphere or human interference. These telescopes will be able to listen to the ultra-low frequency signals from the dark ages of the universe, the period before the first stars were born. We are turning a geological anomaly into a window into the dawn of time. The far side is no longer just a hidden face. It is becoming humanity's most sensitive ear, tilted toward the deepest mysteries of the cosmos. On Earth, the soil beneath our feet is a product of life, wind, and water. It is rounded by rivers and softened by organic decay. But on the Moon, there is no wind to smooth the jagged edges and no water to wash away the grit. Instead, the lunar surface is covered by a layer of regolith, a substance born from 4 billion years of relentless cosmic violence. Because the moon lacks an atmosphere, it is constantly bombarded by a rain of micrometeorites, tiny grains of dust traveling at tens of thousands of kilometers per hour. When these microscopic bullets strike the lunar rock, they don't just break it, they vaporize it and melt it, fusing it into tiny, jagged glass shards. This process, happening trillions of times over eons, has created a soil that is more like crushed glass than Earth. It is a substance that has never been weathered, never been softened. It is as sharp and abrasive as it was the moment it was born. The astronauts of the Apollo missions were the first to encounter the true nature of this gentle killer. To the naked eye, regolith looks like harmless, soft gray flour, but at the microscopic level, it is a nightmare for machinery and biology alike. During the Apollo 17 mission, Harrison Schmitt discovered that lunar dust is sticky due to static electricity. It clung to the spacesuits, worked its way into the joints of the gloves, and eroded the seals of the lunar module. When the astronauts returned to the cabin and took off their helmets, they were hit by a strange, pungent smell like burnt gunpowder. This was the scent of the moon. As they breathed in the fine particles, they developed what Schmitt called lunar hay fever. Their throats became raw, and their eyes grew red and irritated. Because these particles are so sharp and tiny, the human lungs have no way to expel them. If a human were to live on the moon for years without proper filtration, their lungs would eventually be scarred as if they had spent a lifetime in a coal mine. The regolith is the moon's first line of defense, a microscopic army that guards the silence of the craters. But the very properties that make regolith a danger also make it our most valuable construction material. We are now developing the technology to turn this killer dust into the foundation of our future cities through a process called microwave sintering. Because lunar regolith contains high amounts of iron and glass, it reacts intensely to microwave energy. Imagine a giant automated rover equipped with a microwave 3D printer head. As it crawls across the lunar plains, it doesn't need to bring bricks from Earth. It simply heats the dust beneath it, melting the particles together into a solid, ceramic-like pavement. This is the key to the lunar shield engineering. By sintering the regolith into thick walls, we can create habitats that are immune to radiation and micrometeorites. We are learning to use the moon's own scars to protect ourselves. The dust that once threatened the lungs of the Apollo pioneers will one day be the very walls that keep their grandchildren safe in the first lunar cities. We are no longer fighting the moon. We are becoming part of its geology. When we think of the moon, we often think of it as a lawless frontier, a celestial Wild West. But as we move from exploration to habitation, we face a profound philosophical crisis. How do we govern a world that belongs to no one, yet is essential to everyone? In 1967, at the height of the Cold War, the international community signed the Outer Space Treaty. It was a visionary document that declared the moon as the province of all mankind. It prohibited the placement of nuclear weapons in orbit, and most importantly, decreed that no nation could claim sovereignty over any celestial body. For 50 years, this treaty maintained the peace of the moon because there was nothing there that we could easily reach or use. But today, as our technology catches up with our ambition, the silence of the treaty is being tested by the reality of the lunar surface. The challenge is no longer about owning the moon, but about managing its most fragile resources. Consider the permanently shadowed regions at the South Pole. These craters are not just ice mines. They are scientific time capsules that have remained undisturbed for billions of years. If one nation or corporation begins a massive mining operation, the resulting dust and vibration could destroy the delicate chemical records stored in that ice forever. This has led to the emergence of the Artemis Accords and the concept of safety zones. Instead of traditional borders, we are seeing the birth of a new kind of functional sovereignty. These are agreements built on transparency and mutual aid. If a base is in trouble, others are obligated to help. If a resource is being extracted, it must be done in a way that doesn't interfere with the scientific quiet zones of the far side. We are moving from a law of conquest to a law of stewardship. The moon is forcing us to evolve our legal DNA, shifting from a collection of competing nations to a unified, multi-planetary species. Perhaps the most poignant part of this new lunar covenant is the protection of our history. On Earth, the weather eventually erases everything. But on the moon, the footprints of Neil Armstrong and Buzz Aldrin are still there, as crisp as the day they were made. Under the new Lunar Heritage Guidelines, these sites, the Tranquility Base, the Taurus Littrow Valley, and even the crash sites of early robotic probes are being designated as international historical sanctuaries. We are realizing that our first steps into the void are as significant as the first fires tamed by our ancestors. By protecting these fragile marks in the dust, we are signing a contract with our future selves. We are ensuring that 1,000 years from now, a child born on the moon can visit the place where the long journey began and understand that they are part of a story that spans worlds. The Lunar Covenant is more than a set of rules. It is the first constitution of a spacefaring civilization. To truly understand the weight of our presence on the moon, we must look back far beyond the era of rockets and Cold War rivalries. We must look back 300,000 years to the first members of our species standing on the dark, vast plains of the African savanna. To those early humans, the moon was the only light in a terrifyingly dark world. It was the first clock, the first calendar, and the first object of mystery. For millennia, the moon remained an unreachable deity, a silver disk that controlled the tides and the hunt. Our relationship with it was one of observation and awe. We built stone circles like Stonehenge to track its movements. We wrote myths to explain its phases. Every culture, every civilization that has ever risen and fallen on Earth did so under the gaze of this same silent companion. The moon is the only shared witness to the entire story of humanity. When we finally touched its surface in 1969, it wasn't just a triumph of American engineering. It was the culmination of 300,000 years of ancestral yearning. We didn't just go to the moon. We returned to the source of our first wonder. The legendary Konstantin Tsiolkovsky once said, "Earth is the cradle of humanity, but one cannot live in a cradle forever. If the Earth is our cradle, the moon is the threshold of the nursery." It is the first place where we have learned to survive without the protection of our mother planet's thick atmosphere and protective magnetic shield. The moon is a harsh teacher. It has taught us how to recycle our breath, how to harvest the sun, and how to turn sterile dust into shelter. But the most profound lesson the moon provides is one of perspective. From the lunar surface, the Earth does not look like a world of endless resources and invincible strength. It looks like a fragile, glowing sapphire hanging in a void of absolute nothingness. This realization that our entire history, every war ever fought, every love ever shared, occurred on that tiny blue dot is the ultimate gift of the moon. It forces us to grow up as a species. The moon is the testing ground for our maturity. If we can build a sustainable, peaceful civilization on the airless plains of the moon, we prove that we have the wisdom to survive the long journey to Mars and beyond. The moon is not the destination. It is the rite of passage that turns us into a truly spacefaring species. As you drift towards sleep, imagine the moon as it will be 1,000 years from now. By then, the footprints of the Apollo astronauts will be preserved under glass domes, the first monuments of a multi-planetary history. The lunar cities, nestled deep within the basaltic lava tubes, will be vibrant hubs of art, science, and a new kind of culture, one born in low gravity and eternal silence. The moon will have become the great library of humanity. While the Earth is a world of constant change, erosion, and renewal, the moon is a world of preservation. Every digital record, every work of literature, and every DNA sequence of the Earth's biosphere will be stored in the frozen vaults of the lunar poles. The moon is our backup, our insurance policy against the fragility of our home world. If the sun were to flare or the earth to falter, the moon would remain a silent, silver lighthouse, carrying the sum total of human knowledge. It is the guardian of our legacy. As you close your eyes, feel the steady, ancient rhythm of the moon's orbit. It is still there, just as it was for your ancestors, and just as it will be for your descendants. It is the bridge between our past and our infinite future. The journey is long, but the destination is peace. The stars above the moon do not twinkle. They shine with a steady, unwavering light. There is no wind to disturb the dust, no sound to break the stillness. It is the ultimate sanctuary. We are no longer the frightened creatures on the savannah. We are the architects of a new era. As the low hum of the lunar base fades into the background of your consciousness, remember that you are part of this grand story. You are a passenger on a journey that spans 300,000 years and 380,000 kilometers. The moon is watching over you, as it always has and as it always will. Rest now in the magnificent desolation. Rest in the knowledge that the cradle is safe and the threshold is open. The universe is wide, the shadows are long, and the silence of the moon is your lullaby.